It's good, it's good. I like it.
Okay, so the Lewis dot structures. What we're going to be doing is, if you have a formula like this, about 150 years ago, that's all they had was the formula. They didn't have any idea what the structure looked like. So Dr. Lewis and Lewis dot structures came up with this process to estimate what the structure looked like. And he used something called valence electrons. Now, I need a periodic table. Where is the periodic table? All right. Okay, valence electrons are the electrons in the outermost orbital, because those are the ones that do all the chemistry. The ones on the inner orbitals are called core electrons. And those do not do the chemistry. The reason for that is because they're extremely stable. There's no reason for them to react because they're already as stable as they can get. The ones in the outer one are not stable, so they want to react. That's why reactions happens, because those outermost electrons. Now, I'm going to pull up a periodic table, so I've got to insert it here really fast.
That's the key. Old child. That. Yeah. So I didn't think you're still. Even X. So.
Okay, so how do you figure out how many valence electrons are there? Their numbers are sort of different and sort of the same at the same time. Okay, so remember we talked about groups in the periodic table, and the groups have similar chemistry. The reason why they have similar chemistry is because the number of valence electrons are the same. And again, valence electrons determine chemistry. So if they have the same number of valence electrons, that means they have the same chemistry. Now we're going to study this again in Unit 4 in even more detail. Okay, so to figure out how many valence electrons we have, we need to look at that was fun. Where did it go? the wonders of modern technology. Okay, so if we look at, let's say carbon. Okay, remember from last time, every element has two numbers, an integer and a decimal point. The decimal point is the molar mass. That's this guy here. And this is the number of protons and electrons, assuming it's neutral. Okay, that means carbon has a total of 6 electrons. However, those 6 are core plus valence electrons. So, how do you know how many valence electrons there are? You're going to be able to count. This is the hard part of this. Can you count to 92? Probably can. Okay, so we're going to count on this here. Okay, so this is the way you're going to count. You go from left to right. 1, 1, 1, 2, 3, 4. That's how many valence electrons there are. So if carbon has 4 valence electrons, how many core electrons does it have? 2, because 2 plus 4 is 6. Okay, so core plus valence are the total number of electrons. Okay, so for Lewis dot structures, we're only going to use those 4 electrons, not the total 6. If we look at sulfur, for example. Now, again, sulfur is going to have 2 versions of valence electrons. That's why we're not going to use sulfur. But just the way I just counted, though, how many does sulfur have? Okay, well, it has a total of 16. But if we count over 1, 2, 3, 4, 5, that's 6 valence electrons. Or it can have 16 valence electrons, but we're not going to count that part. 6, okay? So, because it's 6 over, how many core electrons does it have? What plus 6 equals 16? 10 core electrons. Okay? Now this is pre-calc math. Some of you in here have already had their calculus series, by the way. Believe it or not. Okay, so that's what we're going to be using, the valence electrons. And that's how you find the number. Now, I have it already for you here. Now, this is a good worksheet to have in dry lab today. The reason for that is the first thing you need to be doing in dry lab is determining and drawing Lewis dot structures. That's the step number 1. So what I have here are the valence electrons for the simple top area of the periodic table. Notice carbon on the left has got 4 valence electrons. Sulfur has got 6, but notice the way they're laid out. Some are singletons and some are pairs. Okay, to make a bond, you need 2 electrons. So if you already have 2 electrons in a pair, that can't bond, except for one exception. And that's a 1A exception, okay? So all we're looking for now are singletons, because they're the bonding electrons. Okay, so what I just said, how many bonds does carbon have? It's going to have, I should say. How many singletons does it have? 4. So how many bonds does carbon have? 4. 1 per singleton. Okay. Now, what's going to happen in the bond, it's going to share another element's singleton. And when those come together, we formed a bond of 2 electrons. But it's a bond of 2 singletons. 2 singletons. Okay, so let's look at oxygen. Oxygen's got 6 valence electrons, 2 pairs and 2 singletons. So how many bonds is oxygen going to have? 2. 2 singletons, 2 bonds. The pairs need to be there to get the electron numbers up, but they don't participate in bonding. Only the singletons. Notice hydrogen. Got 1 singleton. So hydrogen can only bond once. It's one of the simplest ones. Okay, does that make sense? All right, so let's put some stuff together now. Okay, this is a worksheet. I have a couple of worksheets here.
What are those?
Hmm?
Do we have those or just online?
In Canvas.
Okay.
Your dry lab is going to have some similar to this,
Okay.
but you do it the same way. Okay. Now let's do this one. HBr. Okay, step number 1. I have a series of steps for you on a document on Canvas that I usually put up here. So let me put that up here. Okay. So this works for 99% of Lewis dot structures. Now we're going to be looking at Lewis dot structures for the first 3 rows only. Okay. And not doing sulfur. Everything else is fine. After that, things get more complicated because we have more electrons and they start forming different orbitals. That's where the complication comes in, except for the top 3 rows. Those are the ones we're going to be doing in here. Okay. So step number 1, excluding hydrogen and halogens. Remember, halogens are right here. From fluorine down, these are the halogens right here. Okay, so this is a halogen. Halogen. And hydrogen over here on the left. So those are the ones that can only have 1 bond because they only have 1 singleton. The halogens have more electrons than hydrogen, but they're all paired up except for 1. Hence 1 bond. Okay, those are considered the simpler atoms, valence-wise, because they can only bond one way. The more singletons, the more complications arise, like carbon. Carbon, underneath carbon is silicon. Silicon also has 4 singletons. So the more singletons, the more combinations you can have. Okay, so let's go back to the rules now here. That's why I said excluding halogens and hydrogen. start by putting the atom with the most singleton electrons in the center and arrange other atoms around it. Step number 2, connect everything with a pair of singleton electrons, making one bond. Now, carbon's got 4 singletons, 4 bonds. Now, it can have 4 single bonds, or 2 double bonds, or a triple bond and a single bond. Total of 4, though. Okay, then let's start and put that together. So let's put it right up here. Okay, so HBr. H has 1 singleton. Br has 7 electrons, 1 singleton, 3 pairs. Now, we can move the electrons around for convenience. I could have put the singleton on the back side, the top, or the bottom, as long as we have 1 singleton, 3 pairs. Okay, the next step is to connect up the singletons. Well, we have, very simple here, we only have 1. We just made a bond. Now, there are rules for Lewis structures that you need to follow. Now, these rules on number 5 here, verify each has the correct number of bonds. Okay, and this correlates directly from the number of singletons per atom. So if the atom had 4 singletons, 4 bonds. 3 singletons, 3 bonds, etc. Okay, so we have a halogen and a hydrogen. Each of those wants 1 bond. Okay, so here we have halogen bromide. It's got 1 bond. Hydrogen's got 1 bond. So this is a legitimate Lewis dot structure, or legal. Now the next step is to replace the circled singletons with a line. So that's the Lewis dot structure for bromine, but we have to include the non-bonding pairs. And those are extremely important when we talk VSEPR, the valence shell electron repulsion stuff. Okay, so make sure you include, even though the pairs didn't bond, they have to be there. Okay, that's the first example. It's a Lewis dot structure, and it's legal. Okay, did that flow okay? Okay, we need some more examples, right?
Yes, please.
Huh?
Yes, please.
All right, so let's do something with multiple bonds with carbon, for example. So let's do carbon dioxide. So it's 1 carbon, 2 oxygens. Okay, so let's put the one with the most singletons down first, which is going to be carbon. And now we're going to put the other 2 down around carbon. Anywhere you want. I usually put it left and right, but you can put top, bottom. You can put it, anywhere you want. Okay. So we're going to do bromine. Let's put one over here. Oops, not bromine, oxygen. Why did I do that? Now remember, oxygen's got 2 pairs and 2 singletons. Okay. Now the next step is connect the singletons together. All right, so we got 1 here, one there. So every atom has to be connected with at least one bond. Could be two, could be three, not four though. Only one, two, or three. Okay, the next step is to check for singletons not bonded. Are there some singletons not bonded here? Yeah, there are. You've got, here we have one. And here we have one that, notice, if I was going to connect it, it'd be kind of a goofy looking thing. We'd have to go like, and we don't want to do that because that is ugly. So instead of doing that, what we're going to do is we're going to connect up, we're going to make the connections a little differently. So what we're going to do is we're going to bond these two together and these two together, which is nice, much nicer looking. Okay, so no more unbonded singletons. Now, a singleton unbonded is called a free radical. You've probably heard of that. In nutrition, you talk about minimizing free radicals. It causes a lot of stress. You do it by oxidation, antioxidants. And there's a lot of them out there. Vitamin C, antioxidant. But anytime you have an antioxidant, one of the things it does, it scavenges free radicals. The reason why free radicals are bad is they're extremely unstable. To become more stable, what they do is they immediately bond with anything around it. Now, if this happens to be something important in your body, like an enzyme, the enzyme stops working. If the enzyme is something important, like running a nerve, then that nerve stops functioning. So free radicals are bad, bad, bad. You can also get those from too much sunlight. The UV radiation can cause free radicals also. So we don't want to have any free radicals running around here. Okay, so there are no more singletons there or free radicals. So is this a legal Lewis structure? Well, oxygen needs two bonds. Right here. Two bonds. Carbon needs four. Oxygen's got 1-2 bond. That's good. This oxygen's got 1-2. And carbon's got 1-2-3-4. So this is a legal Lewis structure. So the next step is we're going to add lines where the bonds are. Carbon dioxide. Now, the more atoms you have in the formula, the more possibilities exist. And what I mean by that is that you're going to have multiple structures that are also legal, the same combination of atoms. Any questions about this carbon dioxide? Let's look at this is called formaldehyde. Yeah. By counting, looking at the valence electron. No. That's not counting the core electron. That's valence electron. And the core electrons are in addition to that. So we're only looking at valence. So you're going to look at singletons only. Oxygen's got 1-1 pair. Okay, formaldehyde. Who's heard of formaldehyde? Okay, in what context have you heard about it?
It's like the.
That's right. They also use it to make glue. Glue. So if you're in the state of California and you buy a house in the last 25 years and you look at the OSB stuff that they build with, OSB stands for oriented, it's chipboard basically, and they glue it together. The glue is made with formaldehyde. So on your OSB board, the state of California requires them to stamp that this causes cancer. And you're living in this place. What, do you see something wrong with this picture? Now, the formaldehyde, when you first moved, if you buy a brand new house, it's the strongest. And then over the years, it goes away. So if you buy a 20-year-old house, it has significantly less formaldehyde in it than one brand new one. So formaldehyde, and the reason why they use it as embalming fluid in preserving tissue is because the tissue is basically very dead. And it preserves it, keeps it from degenerating further. Now, formaldehyde has something in it called an aldehyde. And aldehyde is very unstable. That's why formaldehyde wants to react because of that aldehyde in there. So let's look at the Lewis structure for this. Okay, what's the most complicated, CH or O? Which has the most singletons in it? Carbon. Okay, what's the simplest one? Hydrogen, because it only has one singleton. So we're going to put the hydrogens on the outside. And it has one oxygen. So let's just put it here. And how many singletons does oxygen have? 2. Now we're going to put them conveniently kind of pointing towards a carbon. And then there's the 2 pair. Okay. Step 2 is connect the dots, connect the singletons. So we got one here, one here, one here. Are there singletons left over? Yes, connect them up as well. Okay, so does carbon have 4 bonds? 1, 2, 3, 4. Yes. Does oxygen have 2? Yes. Hydrogens are 1 apiece. So this is a legal structure. Next thing we do is we put lines. Lines where the bonds were done. So that's what formaldehyde looks like. It's the simplest aldehyde. In fact, that's the chapter I'm on right now over at City, are aldehydes and ketones. Okay. That makes sense? All right. Let's do one that's more complicated than that. C2H6O. Now, you're going to try this on your own. And for those of you who whipped the first one out fast, I want you to do another legal structure. So theoretically, we can do 2 legal structures with this, legal Lewis structures. The more complicated the formula, the more alternative structures work. So go ahead and try this one. And go through the steps. Start with the most complicated one, and go from there. Yeah,
How would we know what? Oxygen. Because the other two wanted. How did you figure that out?
you look at the top of that worksheet I just had. It goes across
Uh,
and just find it there.
uh,
Now, when we get to unit 4, I'm going to show you why there's 2 pairs and 2 singles.
I didn't write it down. I know, I guess I should have.
Well, how about if I,
There we go. Okay.
okay, everyone write these down. Now, this worksheet is also on Canvas Files Unit 2. What?
It's also a file.
Yeah.
Thank you.
That's where I got it from. If not, tell me and I'll get there. It'll take 5 seconds. But I'm pretty sure, because I've been using this stuff forever. This worksheet is like 28 years old. That's how long I've been teaching this. Okay, everyone right, got that down? Okay. So let me write the formula, in fact, it's right here. This is the one we're doing. That one.
So when it has H, then you write out H 6 times, right?
Yeah.
So can you write H? Do you have to have other ones in between?
H, if they only have one bond, they're always on the outside. No exception. So the H's are always on the outside and also the halogens, because they only have one bond.
So it does matter the placement.
It doesn't. Now, your tutor may teach you a different way.
She teaches me how you teach. She
Okay.
teaches me how you talk.
Okay. Because there are 2 ways to do these. And sometimes the instructors do it my way, and sometimes they don't.
The H's, say they're always on the
Oh,
outside.
yeah, because they only have one bond.
But if they stick.
H, 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 H. Yeah. Or you put them all on one side.
Kind of. Where's that? Here.
I think so. Let me see.
Okay, thank you. I think I did the C wrong. I mean, the.
Yeah.
But I gotta do the,
Okay, so there are 3 structures for this. You got one of the 3. You have the hardest one, actually.
the hardest one.
The hardest one, yeah. It's because it's cyclic. See how the carbon-carbon oxygen? Okay. Now, if you've got one done, Try doing another one that's not the same. Because there are three total. At least three. I think there's only three.
It's a one, because it's over. So I do this.
Yeah.
Because they can't look together, and it'll be great. It's one, two, and three. You can make it. Absolutely right. Yeah. I don't get it. It's okay. It's, yeah. Yeah. To the house.
He said.
Yes, I hear what you're saying. No.
He said, one.
I think it's good.
Oh, please, we got this one in Singleton, see? Okay.
And it'd be attached to the.
Okay, so now. Show you on here, like I did here. Maybe that.
Like here.
I don't think you do. Connect the carbons to each other, they're not together. It's just the. Oh, okay, yeah, that makes sense. I see. Okay, so the ones are gonna, there's a lot of ones. Oh, I got it. Ones, all rules.
Is this right?
Okay.
See. Let's just, let's see what. Oh, we're gonna. I was gonna draw the lines, but I don't. That's what I'm changed. Oh. Yeah, then, let's see, it's here. So. Then you gotta.
Yeah, so.
Well, yeah, I don't want to close it that way to the park. I really think much to be positive. Like, right. And if it's just, there's a bad effect, it's a fucking city. So I mean, I'm like, oh, I'm sure we are.
I still.
Just order it out.
Also-
I got something
On.
I. If you think this is Russian. Speak on this way. I don't know how to put swamp. It was confusing, but now I get it. You did this, that's fine. Yeah, like, maybe it's a different. Yeah. The two lines like here, right? Okay. There's one here, there's one here. And then you have green, yeah. And green, so there's a row. Double bonding stuff, but it's. Yeah, well, these are things that don't work. It's not that sort of. It is. And it's like, there's weird things about it, so it makes. And don't have it. I mean, it's part of. Yeah. One, they have these. And it's, there's one other stuff. Really, this year, it's so lost to me. Everything from. It's all because of all the. And that is some. You know, it is to thousands of ignorant people. And it's funny what that. There's one story that was seven months, and it's also thing. What was that? There's. Wait, I got my H's. It's a base. But it's. Wait, before even. Just. Really?
I have no idea where the break is. I was just. It's temporarily this one. Oh, yeah, yeah.
Let's see how he's got it. Now, I just, if you want to find these files, go to Canvas. And at the top here, just, let's see if we go to, up one. Okay, so this is at the. Just do Lewis. Now, the reason why sometimes these structures here are in different units is because I didn't determine the lab schedule. Someone else did. And so it depends on where they put the Lewis dot structure lab is when I have to teach it. So sometimes if I was doing it by myself, see, there's two teachers that teach chemic. When it's just me, I can put any order I wanted. When there's more than one teacher teaching that class, someone else does a schedule, and the stockroom sticks to that schedule. Okay, all right, so that's why just do a search on Lewis, and I'll show you all the files that have Lewis in the title, including the ones you were just looking at a while ago. Okay, all right, so let's go back to working this thing out here. Okay. So let's do two structures. A lot of you, some of you have got all three, some of you have one legal one and other things. Okay, so we've got. All right, so let's start with the carbons first. You don't have to start with the carbons. You should start with something that's more complicated than hydrogen. Don't start with hydrogens. Those go last. So we need to start with the carbons or the oxygen. And since carbon has more singletons than the oxygen, let's go with those first. All right, so we're going to go carbon. Carbon. And the oxygen we can put anywhere, left or the right. Let's just throw it onto the right. And then we have 6 H's scattered around the perimeter. Yes.
But what's it, 5 H's? What's it? Oh, no?
No.
Oh,
6, yeah. 6 is fine.
okay, so
Okay, so let's just scatter them around. And remember now, you can move those around. They're not locked in place. So step 1 is connect everything up with at least one bond. So let's start with the carbons. And we have a hydrogen here.
Oh, so. I inherited it.
Now we're at a conundrum. So we have 2 H's on the right, and we have 2 singletons available, but they're on opposite sides. So let's move this over here. So it can connect up there. And this is going to connect to that. Okay, so that's one legal one. How do I know it's legal? Let's count. Carbon, 1, 2, 3, 4. Carbon on the right, 1, 2, 3, 4. That's good. Oxygen needs 2 bonds. Okay, we've got 1, 2. And the hydrogens all need 1. So that's a legal structure. Let's do the lines in now. Does anyone know what this molecule is? Some drinking alcohol. Ethanol. Okay, so that's That's one. Let's do another one now. Are there any questions how I got that? Okay, so let's put oxygen in the middle this time. Okay, let's connect everything up. We got one. And then we've got these two. And these. Okay, carbon's got four, oxygen's got two, and the hydrogens all have one. So let's put the lines in now. So we have dimethyl ether, same formula, very different chemicals. One is an alcohol, the other is an ether. Okay. Now let's do one more. This time we're going to have the oxygen connect with both carbons at the same time. And why did it do that? Let me get rid of this. Okay, so we're gonna have carbon, carbon. I'm gonna put the oxygen not in between them, but off to the side. And then our six hydrogens. Okay, so let's connect them up now. So what's going on? Yeah. We don't have enough dots to go around. So will that cyclic structure work? We didn't accommodate all the hydrogens. This guy aren't bonded. So this is not legal. Does that mean it's not legal?
Just have to.
Yeah, every dot needs to be connected. Otherwise, you have a free radical. Okay, so what we're gonna do in lab today is we're gonna do Lewis dot structures. So your lab has got two parts to it. So the first thing I want you to do are do the Lewis dot structures all the way through, except for the S's and the ions are optional. Okay, so the next thing we're going to do is we are going to analyze what we got. So, and depends on something called electron repulsion theory. Now, electrons have the same charge as particles repel each other. So what we want to do is we want to lay out in 3 dimensions how these bonds are formed and what are the angles. And there are different versions depending on how many valence electrons are available, how many non-bonding occur, that kind of stuff. Okay, so if we look at okay, let's look at these 3 molecules. Now, the first step, you're going to be doing Lewis structures for these. They'll give you the formula like CH4, NH3, H2O. Do the Lewis dot structure. Then you analyze the Lewis dot structure. First thing is, how many bonds on the first one here? 4 bonds. And we're going to refer to X as number of bonds, E is the number of non-bonds. Okay, so how many bonds do we have over here? Someone already said 4, right? How many non-bonds? 0. Okay, let's look at this one here. This is ammonia, by the way. And I found out today that my cheap spray I made, spiders don't like it either. Okay, so how many bonds do we have on ammonia? 3, 4. If we count the non-bonds as 1. So, okay. What about water? How many bonds?
Yeah.
Non-bonds. Okay, now let's look at the geometry of this combination. This is the VSEPR part. So when we have 4 bonds, no non-bonds, that structure is called tetrahedral. And the bond angle between each of those, C to H, CH, etc., is 109.5 degrees. I'm sorry, what? Yes. So in other words, you have four bonds going into the carbon. When we have 3 carbons going in, 3 bonds going into the middle atom, in this case nitrogen, it is called called trigonal pyramidal. And when we have 2 and 2, that's called bent.
What is this? What is-
Pyramidal, like pyramid, pyramidal.
And that's with 3 bonds.
3 bonds and 1 non-bond. It's important to put the non-bond in there. 3, 1. VSEPR, valence shell electron pair repulsion. You don't need to know that, just know it's VSEPR,
The last one's bent.
bent, B-E-N-T, yeah. Now, this hinges on the Lewis dot structure. Okay, that's why you have to do that first. So. Now, notice we have 4 parts. Here. We've got the top one, 4 H's. The next one down, 3 H's and an electron pair, also 4. And the bottom one, 2 and 2, also 4. What if you don't have 4? What if you only have 3? Let's look at, trying to think of the example your lab uses. Active formaldehyde. Okay. So how many bonds?
2.
Now this is tricky because VSEPR theory requires single, double, and triple bonds to be counted as 1. Think of it as a group of electrons. So how many groups of electrons do we have there?
3.
3. Double bond, 2 singles. Okay, so we've got 3 and 0. Now notice the pairs on the oxygen don't count. This whole thing relies upon something called central atom. By definition, a central atom needs the analysis. Central atom has a central atom has 2 more bonds. So that's why the oxygen here is not a central atom. The only central atom we have in this here is the carbon. Hydrogens don't count because I only got 1. The oxygen has one, only one thing attached to it, carbon. So it's not a central atom. Okay, so when we have 3 and 0, that's called trigonal, again, because it's 3. Planar. Planar means flat. And that degrees is 120. So okay, so a plane tetrahedra 4-0 it's got a 109.5 degrees for each of the connections going into the carbon. If it's trigonal pyramidal, that means it's less than 109.5. Because what happens is the pair, the unbonded pair, pushes those together, the CHs or the NHs. So it's less than 109. On bent, it pushes them even greater. So that's why I put 2 less thans. Now, depending on your next chemistry class, they may have you attach an actual degree to it. Like sometimes they say bent for water is 104 and the other one's 106. It's less. The reason why it's less is because we have distortion caused by the unbonded pair of electrons. They're closer in and they push those other bonds closer together. Hence, the angle is less. Now, with trigonoplanar, the angle is 120. That means that's 120, that's 120, that's 120. Then we have one more. Okay, carbon dioxide. How many bonds we have? We have 4 bonds. How many groups do we have?
2.
2. 2 groups. The double bonds count as 1 group. So we've got 2. How many non-bonds? None. In that carbon, there are no pairs unbonded. Everything has a single bond on it. Okay, and that's called linear. Now, and the angle is 180. Now remember at the top here, I said X's and E's, and X means a bond, E means non-bond. So if we have that's the same as, excuse me, yeah, that's the same as 40. We have no E's. The next one down is 3 X's, 1 E. The next one down is 2 X's, 2 E's. So total of 4 on each one of those. It's just, there's a combination of no non-bonding, 1 non-bonding, 2 non-bonding. So whenever we see this, it goes directly to that. Okay, so this one's going to be, now A is the central atom. So we have central atom, 3X, no E's. Trigonoplanar. And then lastly, we have a 2X, linear. Okay, so we've just gone over how to do the lab today, tomorrow. You're going to go through, do your Lewis dot structures, and you're going to analyze the central atom for X's and E's, and that's going to determine the geometry, tetrahedral, trigonal, pyramidal, or whatever, okay? Now, sometimes there's more than one central atom. Your very last little problem on your lab has got 2 central atoms. So you're going to do this analysis for each central atom. Yeah,
I don't get how you got 2-0 for the last one. So 2 bonds,
yeah, two groups.
so
So
have the,
no, not, I counted the two double bonds as a group. So double bond is a group. It could be a triple bond also, that's a group of one.
because the O have 2, okay. So you have 2, okay, I get it.
Yeah, so when we're doing this part, this Vesper stuff, we're looking at groups. So you're looking at the bonds a little differently when we do the lowest one. So the single bond, that counts as one group. Double bond, one group. Triple bond, one group. And I call them groups because it's a group of electrons. 3 bonds, but it's 6 electrons there, they're in a group.
Okay. So C has, when she wrote it out, it's 4 dots, right? And then O only has 2, so it's just combined for this one, 2. So like C, like this, and then O have the boop, 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 boop.
Or is it just because there's 2 equal signs, that's 1, 2.
Again,
So basically, it's like this, 1 bond, 2 bonds. 1 bond,
But that would make so.
but it's because it's the same. Group.
counting, in this part, we're counting groups, not bonds.
So it's a.
You got lab today, right? Okay. Let's practice this in lab. Now, it's a dry lab, so a couple things, dry lab rules. The main thing are your shoes. Gotta have legal shoes. If you don't have legal shoes, just don't go in the lab to do the lab. Do it out here. Okay? And which is fine with me, doesn't matter. Yeah,
Separate?
yeah, or you can put it in there if you want. Or you can just fill out the lab, the worksheet. Yeah, and then just scan the whole thing.
Any of this.
We'll do it next week.
Because I already wrote the fill up with this one, because I thought it was. There was. I think it's just a routine.
So it's not, it is the.
Was it number 6? So number, no, so there's no print.
Dry lab is no prenup, only what,
Yeah.
so that's what we're doing for this. CD, linear, triple planar, all that. Yeah.
That's the point that